when we look at reactions being reversible, acid-base reactions being reversible, they have to have the ability to come to an equilibrium. Okay? Either you go forward, you go backward, or you float between the two. And in order to float between the two, you have to have equilibrium. Okay? So when we looked way back at Chem 20 and we talked about acids and bases, we studied the different types of acid, ways of naming acids, and we settled on Arrhenius's definition. And so it's that acids have either a hydrogen or hydronium ion, whichever one you want to go with, and they have pHs below 7. Bases are based off of the hydroxide ion, and they have pHs above 7. Okay? And so Arrhenius's definition is still applicable, but it's a little bit limited because that's just to introduce the concept. Along came two guys, and they're called Bronsted and Lowry, and what they did was they extended Arrhenius's definition and helped overcome that barrier of the basicness of Arrhenius's explanation of hydrogen ions and hydroxide ions. So Bronsted-Lowry acids. An acid produces a hydronium ion, and it's called a proton donor. Okay, so we're going to look at kind of the same concepts as redox reactions, where if you gain or lose an electron, we're going to use that same kind of idea. So an acid is a proton donor, okay, because hydrogen is a proton. It's positive. A base can accept that hydrogen ion, and so it's called a proton acceptor, because a base has, in theory, the hydroxide ion, right? And in order for it to get to neutral, it will take on that hydrogen ion that's out there floating around. In order for the acid to donate a proton, you have to have the base present to accept it. So the acid always needs a base, and a base always needs an acid. And because they're dissolved in water, we have that ability to accept and donate protons because water fills in the difference. So if we looked at a first example, hydrogen or cyanic acid acting as an acid. So we would have HCN and water. And I'm going to write water like this because it's easier to see what's moving and what's not moving. As an acid, this is our proton donor. So you're going to end up with, if we donate this hydrogen, we're going to end up with a CN minus. This hydrogen is going to come and join that group. Plus H3O plus. Okay? These are all aqueous states. It's all in water. Now, what about ammonia acting as a base? So, ammonia, which happens to be aqueous, which means that it's in water, it needs to, if it's a base, it needs to accept that hydrogen. And when it accepts that hydrogen, we get the ammonium ion. And we're left with our base, our hydroxide. So these two products here if we have hydronium ion as a product, then it's an acid. If we have hydroxide ion as a product, it's a base. Okay? Question number 2 says, write out the acid-base equilibrium reaction when potassium nitrate is mixed with hypochlorous acid. Actually, let's go back. I want to show you some things that you'll see. When we look at this hydrogen ion here, water, we say that that accepts the proton and that this loss of hydrogen, right? So this donates, or is the proton donor. So this is the acid. The HCN. Yep, the cyanic acid. Yep. This one accepts the hydrogen, and so this makes this the base. Okay? We'll get there. Okay? This one here, this donates the hydrogen, or donates the proton, let's use the correct term. And so it's going to lose it, right? It loses the hydrogen. So yeah, this is the acid. This accepts the hydrogen. Let's go over top. Oops, that wasn't a very good over top. Which means that this is the base. Okay. So same idea that we were looking at. What is the what is the reduction reaction? What is the oxidation reaction? Same kind of concept. What's losing the proton and what's accepting the proton? If we look at hypochlorous acid reacting with potassium nitrate, potassium is just a spectator ion. Okay, so we've got NO2 reacting with HOCl. Well, it's an acid-base equilibrium reaction. What's going to happen? Without looking at anything, go back to Chem 20. In a sense, this would be a double replacement reaction. We're leaving potassium out of the equation, so we would have HNO2 and we would end up with OCl negative, right? Potassium would go there, we would get KOCl. And so this, what happened here? Did we accept the proton or did we donate the proton? This accepted, which makes it the base. HOCl, it donated the hydrogen ion, which makes it the acid. Now, Bronsted-Lowry all right, we'll leave this here. Base and acid. Bronsted-Lowry then expanded their concept. They said, when chemicals only differ from each other by the presence or absence of a single hydrogen pair, we can call them a conjugate acid-base. I don't know if yours might be highlighted and hard to see. This is conjugate acid-base pair. Every acid has a conjugate base, and every base has a conjugate acid. They have partners. Okay? The actual acid in the base is always on the reactant side, and the conjugate acid and conjugate base are always on the product side. ne'er the two shall cross. There's no exception to that rule. That's how it goes. Okay, let's look. Hydrogen bromide is a gas at room temperature, but it's soluble in water. To form hydrobromic acid, identify the conjugate base for hydrobromic acid, identify the other conjugate acid-base pair. So it says hydrogen bromide can dissolve in water. And so what happens? We're going to see the Br happen. Did it gain or lose a proton? Okay, so it lost a hydrogen, so that makes it a acid. Conjugate? Yeah, because they always go together. Water gained a hydrogen. So this is a base. Because they work in pairs, this is the conjugate base, and this is the conjugate acid. Okay? They work together. Okay? They always work in pairs. Now, acids and bases have different strengths. We know that when we look at page 8 and 9, we can see that. We see that these top 6, you can't see them. These top 6, we call them strong acids, and they dissociate. These ones here, underneath the gray, we call these weak acids. Not necessarily. So these would still be weak bases. Strong bases are like sodium hydroxide, calcium hydroxide. Those are what we call strong bases. Okay, these ones are weak. So some acids donate protons more easily, and some bases accept protons more easily. If you have one that's going to accept or donate protons more easily, so strong acids are found at the top left-hand side of the table and decrease in strength as you go down. That sounds familiar. When we go like this, here's our acids, and then this one says conjugate base. This is stronger and gets weaker. Okay, stronger bases are found at the bottom and get weaker as they go up. We've already seen that pattern. Strong goes up. On the base side. Okay. Bases, strong bases have a really small Ka value, and strong acids have a really large Ka value. So when we look at page 8 and 9, here is phosphoric acid. This is something that we find in pops that are dark in color, so like Pepsi, Coke, Dr. Pepper, those kinds of pops, they have phosphoric acid in them. This has a 6.9 times 10 to the 3 Ka. This is an acid constant column. If I look at it's on here somewhere. Here's another food one. Lactic acid, right? You're familiar with that from Bio 20, where you get the lactic acid buildup in your body and you get the lovely cramps in your muscles. This is got a 1.4 times 10 to the negative 4. It is weaker than phosphoric acid. We ingest phosphoric acid and we ingest or produce lactic acid, so they're not acids that will burn us and peel our skin off. They're overall, this is weak. If we can eat it, it's weak. If we produce it in our body, it's weak. I mean, we have pyloric acid in our stomach. That's not weak. When that stuff gets let loose, we get ulcers. Okay? But for the most part, these are weak acids. If multiple acids and bases are present in a container, it will be defined by the strongest acid and or the strongest base. Okay? In an acid-base reaction, the reaction will favor the side of the reaction that contains the weaker base or the weaker acid. So let's look at some predictions. There's 2 in here. And these are all aqueous. I'm just being lazy. Okay, first one's first. Sulfate ion reacting with, what's this guy called? This is organic chem. Methanoic acid, otherwise known as acetic acid. This? No, this is just a print. It's just a line. Okay? And then this is acetate ion. So, what happened here? It gained a hydrogen. That makes sulfate what? Base. What happened there? Lost a hydrogen, donated. In this unit, it's accept and donate instead of loss and gain. But it donated a hydrogen, which makes this the acid. Okay, if this is the base, this is the conjugate acid. If this is the acid, this is the conjugate base. Now what we need to do is we need to look. I'm going to just use my own cheat sheet. Raise this up. All right. So now what we need to do is we need to find the sulfate ion. It's up here. Same way we worked that other chart. Here's my sulfate ion. And CH3COOH right here. Okay? In the redox world, this would be non-spontaneous, but we're not looking at that. Which one is stronger? So here's sulfate, which means that here's the acid here, and here's the base here. This is HSO4 is higher than CH3COOH. Which one is the stronger acid? HSO4. So this is the stronger acid. This is the weaker acid. when I look back here, here is again SO4, HSO4. Where did you go? Right here. Here's acetate ion, and here's sulfate ion. Which one is stronger? Acetate, because it starts at the bottom and it goes up. Okay? This is the stronger base. This is the weaker. Oh, this should be, use the wrong words. Base, acid. Sorry, I had those backwards. All right, it says, in an acid-base reaction, the reaction will favor the side of the reaction that contains the weaker acid or base. What will this favor? Yep. Right, let's look at a second equation in here. Yeah, I said there was 2 in here. All right, let's look at what happened. Oh, yep. What happened here? It donated, making this the, if this donated the proton, this makes it acid. What happened here? Whoa, look, it went from NH3 to NH4. It accepted, right? Which makes this the base. Which makes this the conjugate acid and makes this the conjugate base. So then we go back to our chart. Here's H2PO4. Down here in HPO4. H2PO4 negative is up here as well, but we're not looking at phosphoric acid. We're down here at H2PO4 minus and HPO4 2 minus. And NH3 and NH4 plus. Right here. Here's our, here, well, still can't see. Here's our group right here. H2PO4 minus or NH4 plus. Okay. H2PO4. This is the stronger acid. This is the weaker acid. Okay. Now, NH3 and NH3 and HPO4. NH3. This is the stronger base.
You have like a strong base, weak acid produces a weak acid strong base.
Not typically. What is this favor? Yep.